Now what we're going to be discussing is what's called the Rayleigh Criterion. And previously what we did is we passed light through a single slit and we looked at the dark spots. You could also look at the light spots or the fringes as well. And in that case, we really didn't talk about the shape of the slit. Now in this case, we're talking about a circular aperture where it's not going to be rectangular, it's going to be circular. So it's going to have a particular diameter. Now what the Rayleigh Criterion states is that it's the resolving power that is given as the smallest angle between two sources that can be seen as distinct. So what we have is we have a green object whose light is passing through a aperture and it's given some kind of image. And this happens to be the maximum intensity of that image. Likewise, we have object 2 whose light is going to pass through the exact same aperture, and this would be its maximum intensity. Now, as this angle gets very, very small, these two peaks are going to overlap and they will no longer be distinguishable. So you want this angle to be as large as possible such that you have the greatest amount of resolving power that exists. So once again, as this angle gets small, these intensities are going to overlap, and thus the purple object and the green object are not going to be distinguishable anymore because the light is going to be overlapped. As this angle is larger and larger and larger, they will be separated, and thus they'll have greater resolving power. Now the equation that we will use for this is theta min, which is going to be in radians, is equal to 1.22 lambda divided by the diameter of the aperture. And so for the very first question, we're going to be looking at the human eye. The human eye works the exact same way. The pupil is really the aperture for the eye. And so the question reads as such: limit of human vision, which is most sensitive to the wavelength of 550 nanometers. So the wavelength we're going to be looking at is 550 nanometers. Now, in A, we want to find theta min when the diameter of the pupil is 1 millimeter. So that's going to be when it's really bright out and the pupil is really, really, really small. So we want to find what the angle minimum for that is. And so theta min is equal to 1.22 times the wavelength, which is 550 nanometers, divided by our diameter, which is 1 times 10 to the 6th nanometers. So I simply converted the millimeters into nanometers. This becomes 1 times 10 to the 6th nanometers. Now remember, this is going to be in radians, and that's going to be equal to 0.671 times 10 to the minus 3 radiant. If we want to convert that into degrees, we'll take 0.671 times 10 to the minus 3 radians and multiply it by 180 degrees divided by pi. And for that, what we end up getting is we get 0.0384 degrees. Now for B, what we're going to look at is when the diameter is 8 millimeters. So this would be, for instance, if it's dark out and the pupil is going to be very, very large. Now this is going to be equal to 8 times 10 to the 6th nanometers. And so once again, we're going to find our theta min, and that's going to be equal to 1.22 times 550 nanometers divided by 8 times 10 to the 6th nanometers. And that is going to be equal to 83.9 times 10 to the negative 6th radians. We can do the exact same treatment what we did up here, and we find out that this is going to be equal to 4.807 times 10 to the negative 3 degrees. So what this tells us is that when our diameter of the pupil is going to be at 8 millimeters, so late at night, this this theta is going to be very, very, very small, such that these two objects will probably not be able to be resolved. We won't be able to resolve them at all. As opposed to when our pupil is 1 millimeter, this theta is going to be very large, bringing those intensities out greater, and thus it will be better for us to resolve them. So you have better resolution when your pupil is very, very small, as opposed to when the pupil is very, very large. If you have any questions on Rayleigh criterion, please let me know.